This is Manish Zada from third year chemical engineering department. My roll number is BT22 CME 043. Today I'll explain you some questions on the shell balance problems with heat generation. This is a transport phenomena project, which is all depends on this explaining the questions. So let's move to question one. That is steady state conduction through the plane wall. Uh, A plane wall of thickness L and thermal conductivity K is maintained at two constant surfaces, temperature T1 on the left face at x is equal to 0 and T2 at the right face at x is equal to L. Assume one-dimensional steady state heat conduction with no internal heat generation. Derive the temperature profile in the wall using the shell balance method and determine the heat flux to the wall. So this is the question in front of us, explaining everything, how how all the given are for us, and assumptions are right here. That is steady state, one-dimensional conduction, constant thermal conductivity K, no internal heat generation. Step one: understand the physical setup. You have a flat wall of thickness L with a thermal conductivity K. The one side of the temperature is T1 at x is equal to 0. The other side of is at temperature T2 at x is equal to L. We assume steady state, no internal heat generation, and constant K. These are all the these are all the information that is given inside the question to us. Step one is understanding that. Step shell balance derivation. Let us derive the temperature profile using a shell balance. We take a thin slice of thickness delta x at position x. Heat flux at position x, Qx is equal to minus k dt by dx. Total heat entering area A. Q in is minus ka dt by dx modulus of x. Sorry, heat flux at position x plus delta x. Q out in minus ka dt by dx modulus of x plus delta x. These are the two way Q heat entering and heat outside for the both the outlet. Energy balance Q in minus Q out is equal to rate of energy accumulation. Energy balance Q in minus Q out is equal to rate of energy accumulation. Since we assume steady state, Q in minus Q out is equal to 0. So Ka minus Ka dt by dx modulus of x plus Ka dt by dx modulus of x plus delta x is equal to 0. When we take the both equations at a side, Q in and Q out, and equate it, we get this equation, which is minus Ka dt by dx modulus of x plus Ka dt by dx modulus of x plus delta x is equal to 0. Divide a delta x, take the limit x at as x delta x is equal to 0. We get d by dx upon dt by dx is equal to 0. That is after solving that, we get d square t upon dx square is equal to 0. Step 3, solve the differential equation. D square t by dx square is equal to 0. And after integrating once, we get dt by dx is equal to C1. After integrating again, we get Tx is equal to C1x plus C2. Step 4, apply boundary conditions. T naught is equal to T1. After that, we get C2 minus T1. TL is equal to T2. After we get T2 is equal to C1L plus T1. T1 is equal to T1 minus T2 minus T1LT in the modulus of L. Step 5, final temperature profile. Tx is equal to T1 plus T2 minus T1 Lx. This is a linear profile for T1 to T2. We get a graph here, which is a linear graph for T1 and T2. Step 6, heat flux and heat rate. From Fourier's law, we get Q is equal to minus Ka K dt by dx is equal to minus K T2 minus T1 L is equal to K T1 minus T2 L. This is the heat flux in watt per meter square. Multiply by area A to get the total heat rate. That is Q is equal to small q into A. That is Ka T2 minus T2 minus T1 by L. This is the final answer that we get from the various steps that we did. That is, the first step was understanding the physical setup here. Second step was shell balance derivations, all the derivatives that were used in this process. Step 3, solve the differential equations. Step 4, apply the boundary conditions. Final temperature profile is made, and after that, heat flux and heat rate are removed, are being extracted from the question for the final answer. Question 2, radial conduction through a cylindrical wall. First, we'll read the question and then we'll again go through all the steps that we have gone again. A long hollow cylinder with the inner radius R1 and outer radius R2 is subjected to steady state radial heat conduction. The inner surface is maintained at temperature T1 and outer is at T2. Derive the temperature profile using the shell balance. This was a very good. This is a very good question. Let's go on the assumptions right now. Steady state, one-dimensional radial conduction, no internal heat generation, constant thermoconductivity. All the assumptions and questions are very nicely explained. So let's move on to step one, understanding the physical setup. You have a cylindrical pipe or a shell. Okay. Inner radius is R1, temperature T1. Outer radius is R2, temperature is T2. The length of cylinder is L. Thermal conductivity is K, assumed it's constant. We have assumed steady state, 1D radial conduction, and no internal heat generation. Step 2, set up the shell balance. Take a thin cylindrical shell at radius r and thickness delta r. Surface area at radius r is A is equal to 2 pi rl. Heat rate entering the radius r is Q in is equal to minus K into A into dt by dr 2 and the modulus of r. Q in is equal to minus K 2 pi rl into dt by dr modulus of r. Heat rate exiting the radius r plus delta r. Similar to that, Q out is equal to minus K into area into dt by dr modulus of r plus delta r. Q out is equal to minus K 2 pi r plus delta r L into dt by dr modulus of r plus delta r. Energy balance. No accumulation at steady state. Q in minus Q out is equal to 0. Because of steady state, we assume Q in minus Q out is equal to 0. So after that, we equate it, derive the, derive the differential equation, simplifying and using the fundamental theorem of calculus. D by dr is equal to r dt by dr is equal to 0. This is governing equation for the radial conduction in a cylinder. Step 4. Step 4. Solve the differential equation. Start from d by dr. R dt by dr is equal to 0. Integrate after integrating once, we get r dt by dr is equal to c1. That is dt by dr is equal to c1 by r. After integrating again, we get dr is equal to c1 ln r plus c. Step 5 is apply boundary conditions. R is equal to r1, t is equal to t1 at r2, r is equal to r2, t is equal to t2. Apply first boundary conditions. Applying first boundary conditions, that is t1 c1 into ln r1 plus c2, that's the equation 1 that we get. Applying the second boundary condition, that is t2 c1 ln r2 plus c2, that's this equation second. Subtracting 1 from 2, t2 minus t1, and that is equal to t1 ln r2 minus ln r1 is equal to c1 ln r2 r1. That gives c1 is equal to t1 minus t2 ln r2 by r1. Back substituting to get c2. That is c2 is equal to t1 minus c1 ln r1. This is the c2 substitution we get. Step 6. Final temperature profile is tr is equal to t1 plus t2 t1 plus t2 minus t1 by ln r2 by r1 into ln r by r1. This is a logarithmic temperature profile in the radial direction. So in the previous question we saw there was a linear profile. Now we'll get a logarithmic temperature profile in the radial direction. Now let's go to step 7, that is heat flux and heat rate. Heat flux radial, that is QR is equal to K dt by dr is equal to K T2 minus T1 ln R2 by R1 into 1 by R. This varies with the radius, that is not constant across the wall thickness. The total heat rate is the same across the wall. Any radius commonly at R is equal to R1, Q is equal to QR into A, that is equal to minus K into 2 pi RL into dt by dr. Substitute dt by dr is equal to T2 minus T1 ln R2 by R1 into 1 by R. Q is equal to 2 pi KL T1 minus T2 ln R2 by R1. This is the total heat transfer through the cylindrical wall. So this was the second question that we solved. We'll go once again for all the steps, understanding the this was the radial conduction through a cylindrical wall. Step 1 was understanding the physical setup. Step 2 was a setup of the shell balance. So understanding the taking shell balance, we went through all the steps to equate Q in, Q inside and Q outside. When after derivation, the step 3 was derive the differential equation. That is, we get a radial conduction to for understand this is the we get the equation for radial conduction in a cylinder. Step 4, solving the differential equation. We get after integration, we get the two equations here. Next, boundary conditions. Applying the boundary conditions, we get the value of C2 in this, and final temperature profile, that is logarithmic here. After that, we will understand there's a logarithmic temperature profile in this question where it is in the radial direction. Step 7 is heat flux and heat rate. We also we got the total heat transfer rate to cylindrical wall at the end of this question. So uh, next question is problem third, that is radial conduction through a spherical shell. A spherical shell has inner radius R1 and outer radius R2. The inner surface is held at T1 and the outer radius at T2. Assume steady state radial conduction with a with no internal heat generation. Find TR using the shell balance. Assumptions: steady state, one dimensional radial conduction, constant thermal conductivity, and no internal heat generation. We'll directly move to step 1, that is understand the physical setup. We are analyzing a spherical shell here, that is inner radius is R1, temperature T1, outer radius R2, temperature T2, thermal conductivity K, that is constant. We assume steady state radial symmetry, temperature depends on only on R, no heat, internal heat generation, constant thermal conductivity. Step 2, setup of the shell balance. Take a thin spherical shell from the radius R plus delta R to R plus delta R on the surface area of the radius R. 4A is equal to 4 pi R square. Heat rate entering the radius R, that is Q in heat entering, that is Q in, is equal to minus K into A into dt by dr modulus of R. That is Q in is equal to minus K into 4 pi R square into dt by dr modulus of R. Heat rate exiting the radius R plus delta R, Q out is equal to minus K into 4 into area into dt by dr modulus of R plus delta R. Q out is equal to minus K 4 pi R plus delta R on pi raised to 2 into dt by dr modulus of R plus delta R. Step 3, energy balance. Assume the steady state, no energy accumulation, Q in minus Q out is equal to 0. Take the limit delta R is equal to 0. So we get d by dr is equal into R square dt by dr is equal to 0. This is the governing equation for the radial conduction in a sphere. So you have to remember, this is the governing equation here. Step 4, Solve the differential equation. We solve d by dr r square dt by dr is equal to 0. Integrate once r square dt by dr c1 is equal to dt by dr up is equal to c1 by r2 r square. Integrate again dr is equal to minus c1 upon r plus c2. Step 5. This is an interesting one. Apply boundary conditions. Tr1 is equal to T2 and Tr2 is equal to T2. Apply at R is equal to R1. T1 is equal to C1 minus C1 upon R1 plus C2. Apply at R equal to R2. T2 is equal to minus C1 upon R square plus C2. This is the second equation. Subtracting 1 from 2, T2 minus T1 is equal to C1 1 upon R1 minus 1 upon R2 is equal gives C1 is equal to T1 minus T2 1 upon R1 minus 1 upon R2. T1 minus T2 R2 minus R1 upon R1 R2 gives R1 R2 into T2 minus T1 upon R2 minus R1. Then use this the equation 1 is used to solve the C2. After that we get C2 is equal to T1 plus C1 upon R1. Step 6, final temperature profile. Substitute into Tr is equal to minus C1 R plus C2, or directly Tr is equal to T1 plus T2 minus T1 upon 1 upon R2 minus 1 upon R1 into 1 upon R1 R minus R1 upon R1. This gives the temperature at radius R between R1 and R2. This is the equation we have to remember, and we have to understand this is the equation that we get. Step 7, heat flux and heat rate. Heat flux is Qr is equal to minus K dt by dx is equal to K C1 R2. Total heat rate, we have to use Q is equal to QR into A. K C1 upon R2 K C1 upon R2 is equal into 4 pi R square, that is equal to 4 pi K C1. Substitute C1 is equal to R1 into R2 T1 minus T2 R2 minus R1. Q is equal to 4 pi K into R1 R2 into T1 by T2 upon R2 by R1. After substituting this, we get Q, that is 4 pi K into R1 into R2 into T1 minus T2 upon R2 minus R1. This was the third question of a very same seven of 7 steps actually. We'll go through the steps again for understanding the question nicely. Understand the physical setup. Understanding the physical setup is mainly giving the all the information inside the step 1 and mainly summarizing all the question. Step 2 is setup of the heat shell balance. Step 3 is the energy balance. Step 4 is solving the differential equation. We'll get two integration equations here. Step 5, applying the boundary conditions. We get C2, the value of C2, that is T1 plus C1 upon R1. Step 6, final temperature profile. We get a equation that if we solve it, we will get a profile that is logarithmic. Step 7, heat flux and heat rate. And Q we get after this 4 pi K into R1 into R2 T1 minus T2 upon R2 minus R1. So we'll move to the next question, that is problem 4, plane wall with internal heat generation. A wall of thickness L generates heat at a uniform rate Q, that is watt per meter cube. The thermal conductivity K is constant. The wall surface are maintained at T1 x is equal to 0 and T2 x is equal to L. Find Tx is using the shell balance. Assumptions: steady state, one dimensional flow, constant K, uniform internal generation. Step 1, physical setup. In the step one, we'll mainly write down all the given in the question and understand and summarize the question easily. Physical setup, we now have a flat wall of thickness L, uniform heat generation Q, that is watt Q dot is equal to watt per meter cube, thermal conductivity K, boundary conditions, temperature at both surfaces known as T naught is equal to T1 and TL is equal to T2. Step 2, shell balance and heat generation. Take a thin slab of x2 del x plus delta x, area of surface A, heat inside. That is Q in is equal to minus Ka dt by dx, modulus of delta x. Heat out is Q out minus Ka dt by dx, modulus of x plus delta x. Heat generated inside the wall. Q generation is equal to Q into A into delta x. Energy balance here in understanding the steady state is Qin minus Q out plus Q generation is equal to 0. Divide by A delta x, take limit of delta x is equal to 0, delta x that is 0, K dt upon K d square t upon dx square plus Q dot is equal to 0. That is d square t upon dx square is equal to Q dot upon K. Step 3. Solve the differential equation here. We get d square t upon dx square is equal to step 3. Solve the differential equation, that is d square t on dx square q dot k. Integrate once. We get dt by dx is equal to q dot kx plus c1. Integrating again, we get dx q dot by 2kx 2kx square plus c1x plus c2. Step 3 is a very complicated one, as differential equation is very much different than we have faced in the other questions. But we have to move to the next step, that is applying the boundary conditions. T naught is equal to T1 and C2 is equal to T1. TL is equal to T2. CL is equal to T2. T2 is equal to Q dot upon 2K L square plus C1L plus T1. After solving for C1, we get C1 is equal to T2 minus T1 minus Q dot by 2K L square by L. Step 5, final temperature profile. Substituting everything in Tx is equal to Q dot upon 2kx square plus T2 minus T1 minus Q dot 2k L square upon L bracket x plus T1, we get this is a parabolic temperature profile. The curve depends on Q dot and boundary temperatures. As this after solving this equation and putting the values here, we have got a parabolic temperature profile for the and the curve depends on Q dot and boundary temperatures. Sorry. Step 6, maximum temperature. To find the maximum temperature, take derivatives. That is dt by dx is equal to Q dot upon kx plus c1. Set dt by dx is equal to 0 to find the peak. X max is equal to kc1 upon q dot is equal to minus k upon q dot into t2 minus t1 minus q dot upon 2k l square into l bracket close. This is the location where the temperature is highest, usually near the center if t1 is equal to t2. This is the final answer that we get after solving the 6 to 7 steps. But last step is remain after solving the 6 steps. We'll once go through all the steps. Physical setup, that is we have got after understanding all summarizing the questions. summarizing the question in some points. After that, next is step 2, shell balance and the with the heat generation. Uh, Step 3, solving the differential equation. We get the two integration after two types integration. We get this equation here. Step 4, applying the boundary conditions. We get a value for C1 here, that is T2 minus T1 minus K Q dot upon 2 K L square. Step 5, that is final temperature profile. Substituting everything, we get a parabolic temperature profile, and the curve depends on Q dot and boundary temperatures. Step 6, maximum temperature. Maximum temperature we get here is between this highest here, that is X max is equal to minus KC1 upon Q dot. If we solve it further, we get minus K upon Q dot into T2 minus T1 minus Q upon 2K L square into L. This is the location where temperature is the highest, usually near the center, if T1 is equal to T2. Okay, we'll move to the next problem. This is a very much derived question here. Problem 5 is unsteady heat conduction in a slab. Deriving heat diffusion equations. Derive the unsteady state heat conduction equation in a plane wall through a shell balance. Okay, it's a derivation. So first, again, we have to write the physical setup for the step 1, what we have understood. Step 1 is physical setup. A solid or hollow cylinder, inner radius R1, outer radius R2, uniform heat generation, that is Q dot in watt per meter cube. Thermal conductivity K is constant. Steady state radial symmetry, no axial or angular variation. Step 2, start the shell balance. Cylindrical coordinates. Take a thin cylindrical shell of thickness R, delta R. Heat inside, that is Q in is equal to minus K into area into dt by dr modulus of R. That's the limits. Q in is equal to minus K into 2 pi RL into dt by dr modulus of R. Heat out, that is Q out is equal to minus K into area into dt by dr modulus of R plus delta R. Q out is equal to minus K into 2 pi R plus delta R bracket L into dt by dr modulus of R plus delta R. Heat generated, that is Q generation, is equal to Q dot into volume. What we get here is Q dot into 2 pi RL into delta R. Energy balance, steady state. We get Q in minus Q out plus Q generation is equal to 0. This is a very basic one. Uh, it's a concept, so we have to use that concept here. Divide by 2 pi L delta R and take limit delta R, that is 0, minus K d by dr and into R dt by dr bracket Q dot R is equal to 0. Let's move to step 3. Rearranging Rearranged governing equation. After solving equation in the upper page, we get dt d by dr into r dt by dr bracket is equal to Q dot R pi k. This is differential equation governing radial heat conduction with the generation. Step 4, solving the differential equation. After integrating once the governing equation, we get R dt by dr is equal to minus Q dot upon 2K into R square plus C1, that is dt by dr Q dot 2K R plus C1 by R. Integrating again, we get Tr is equal to minus Q dot 4 pi 4K R square plus C1 ln R plus C2. C1 and C2 are the constants. Step 5, applying boundary conditions. Case 1, both the temperatures known. If Tr1 is equal to T1 and Tr2 is equal to T2, then you solve for C1 and C2 using T1 is equal to minus Q dot R R1 square upon 4k plus C1 ln R1 plus C2. And for T2, we have to solve minus q dot R2 square upon 4k plus C1 ln R2 plus C2. Subtracting the equations eliminates C2, and after solving for C1 by back substituting we get C2 here. That is, step 6 is a final temperature profile. Our general solution, Tr is equal to minus q dot R square upon 4k plus C1 ln R plus C2. This temperature, this gives the temperature radius R. So we have seen the C1 and C2 as the constants here, and after solving this we get a very consecutive graph of the temperature. Step 7, special case, that is cylinder with insulated outer surface. Let's say inner surface Tr1 is equal to T naught, and outer surface, instead of dt by dr, modulus of R2 is equal to 0. From dt by dr is equal to q dot R by 2k plus C1 by R gives dt by dr modulus of R2 is equal to 0. And after solving this, we get q2 q dot R2 by 2k R square by 2k plus C1 upon R2. C1 is equal to q dot R2 square upon 2k. Now plug into Tr is equal to minus q dot R square upon 4k plus q dot R2 square upon 2k ln R plus C2. When we apply T R1 is equal to T naught, and we get C2 here after solving it linearly. So this was the fifth question. This was a very different question than other that we have already solved. It wasn't complex one, but it has a different approach other than this. We'll see the steps again. First step was physical setup. In the physical setup, we saw all the summarized data inside the question here. Step two, start the shell balance. Say cylindrical coordinates. Take a thin cylindrical shell. Taking a thin cylindrical shell. Step two was the start with the shell balance. Step three was rearranged governing equation. This is the direct differential equation governing radial heat conduction with generation. Step 4 was solving the differential equations by and getting Tr is equal to minus q dot, like the other q dot upon 4 k R square plus C1 ln R plus C2. This is step 4. Step 5 is applying boundary condition. After applying the boundary conditions, we get C2 after back substituting it. Final temperature profile comes from Tr is equal to minus q dot R square upon 4k plus C1 ln R plus C2. And step 7 is special case here, cylinder with insulated outer surface. Let's move to the sixth question. So we have completed the 5 questions. We are halfway through. There are various questions from various topics here. In the problem 6, we are going to cover composite wall with 2 layers. A wall is made of 2 layers. Layer 1 is thickness L1, conductivity K1, and layer 2 is thickness L2 and conductivity K2. Left side at T1, right side at T2, interface temperature is Ti. Find the temperature profile and heat flux using the shell balance. So again, the step 1 that we are going to solve here is physical setup. We have a spherical shell. Inner radius is R1, outer radius is R2. Uniform heat generation, that is uniform heat generation, Q dot is equal to weight watt per meter square, thermal conductivity K constant, steady state, radial symmetry, no angular or azimuthal variation. Step 2, start with the shell balance in and spherical coordinates. Take a thin spherical shell from R to R plus delta R. Surface area at radius R is A 4 pi R square. Heat inside Q in is equal to minus K 4 pi R square into dt by dr modulus of R. Q out is equal to Q in Q out is equal to 4 minus K into area into dt by dr modulus of R plus delta R. Q out is equal to minus K 4 pi R plus delta R bracket square into dt by dr modulus of R plus delta R. Heat generated, that is Q generation, Q dot into volume is equal to Q dot into 4 pi 3 pi bracket R plus delta R cube minus R cube bracket close, which corresponds to Q dot into 4 pi R square delta R. Step 3, energy balance steady state, that is Q in minus Q out plus Q generation is equal to 0. Divide by 4 pi delta R, take limits R to delta R to 0. Minus K d by dr R square dt by dr plus K2 R square is equal to 0. D by dr into bracket R square dt by dr is equal to Q dot K R square. Solve the differential equation d by dr R square dt by dr is equal to Q dot K R square. Integrating once, R square dt upon dr is equal to integration of Q dot R to R square dr by K is equal to Q dot R cube upon 3K plus C1 is equal to dt by dr Q dot R by 3K plus C1 by R square. Integrating again, dr is equal to integration of bracket Q dot R upon 3K plus C1 R square bracket dr is equal to Q dot R square 6K minus C1 upon R plus C2. Applying the boundary conditions, case both surface temperature known, Tr1 is equal to T1, Tr2 is equal to T2. Use T1 is equal to Q dot R1 square by 6K minus C1 upon R1 plus C2. T2 Q dot is equal to R2 square upon 6K minus C1 by R2 plus C2. Subtract the two equations to eliminate C2. C2 T2 minus T1 is equal to Q dot by 6K into R2 square minus R1 square minus C1 1 by R2 minus 1 by R1 is equal to C1 Q dot R2 square minus R1 square by 6K minus T2 minus T1 upon 1 by R2 minus 1 by R1. Then plug back into one equation to get T2. Step 6, that is final temperature profile, we get Tr is equal to Q dot R square upon 6K minus C1 by R plus C2. This gives temperature at any radius R between R1 and R2. Special case again, step 7, solid sphere with a surface temperature. Say center is at R is equal to 0, surface at R is equal to capital R, Tr is equal to Ts. At R is equal to 0, temperature temperature must remain finite, number 1 by R term. Then set C1 is equal to C1, set C1 is equal to 0. Use boundary conditions. Tr1 is equal to Q R square capital R square upon Ck plus C2. C2 is equal to Ts minus Q dot R square upon 6K. Final expression, Tr is equal to Q dot by 6K R square minus capital R square plus Ts. So this was a question that we have solved, the sixth one. We'll go through it again, understanding all the steps. And this question was on composite wall with two layers. So step one was physical setup. Understanding all the points that were given in the question and summarizing it down to 4 to 5 lines. Step two is start the shell balance in in spherical coordinates using the area in various ways and writing it down. Step three was energy balance in the steady state. Uh, we use the limits and understand the answer there, understand the equation there. Step four was the solving the differential equation and integrating is twice to get equation for the temperature profile. Step five was the applying the boundary conditions. After applying the boundary conditions, we get C2 here. After getting C2, the step six is final temperature profile for TR is equal to Q dot R R square 6K minus C1 by R plus C2. And this is the radius R between R1 and R2. Step 7 is special case for solid sphere and surface temperature. It was a great question. Let's move to the seventh one. Heat conduction in a fin, that is constant area. A fin of uniform cross-sectional area A, thermal conductivity K, and length L extends from a hot wall at temperature T TB into a cooler environment. The fin loses heat by convection to surroundings at T infinite with heat transfer coefficient H. We'll write down the assumptions here. S- Steps steady state 1D 1D conduction along the length of the fin, constant K and A, heat loss by convection from the surface. Step 1 is physical setup, wall of total thickness 2L, symmetric about the center, uniform heat generation Q dot, thermal conductivity K, boundary conditions, symmetry at x is equal to 0, temperature known at x L x is equal to L, PL is equal to PS. We only need we only need to analyze x is equal to 0 and xl is equal to due to symmetry. Step 2, governing the step 2 is governing equation first from the shell balance. d d square t upon dx square is equal to minus q dot by k. This comes from a standard shell in Cartesian coordinate with internal generation. Step 3. Step 3, solve the differential equation. First integration is dt by dx is equal to minus q dot x by k plus c1. Second integration, Tx is equal to minus q dot x plus minus q dot is equal to x square upon 2x k plus c1x plus c2. Step 4 is apply boundary conditions, symmetry at the center at x is equal to 0, dt by dx. So dt by dx, modulus of x is equal to 0 is equal to minus q dot is 0, q dot 0 is equal to k upon c1 is equal to 0. That is c1 is equal to 0. Surface temperature at x is equal to L, TL is equal to Ts. Plug into the equations. Ts is equal to minus q dot L square upon 2k plus C2. That is C2 is equal to Ts plus q dot L square by 2k. Step 5, final temperature profile. Tx is equal to minus q dot x square upon 2k plus Ts plus q dot Ts is plus q L square upon 2k. Tx is equal to q dot by 2k L square minus x square plus Tf. This is the parabolic temperature profile with the maximum temperature at the center x is equal to 0. Step 6, sorry, there is so in these questions we understood all the steps and parabolic temperature profile is obtained. Step 1 is a physical setup. Step 2 is governing equation from the shell balance. Step 3 is solving the differential equation. Step 4 is applying the boundary conditions here. And step 5 is the final temperature profile that is parabolic in nature. At the center, x is equal to 0. Problem 8. heat conduction in a cylinder with the internal heat energy. A solid cylinder at a radius r generates heat at a uniform rate q dot watt per meter cube. The surface is maintained at temperature Ts. Assumptions: steady state, radial symmetry, constant thermal conductivity. Step 1 is physical setup. A solid cylinder of radius r, uniform heat generation q dot watt per meter cube, constant thermal conductivity K, steady state heat conduction. Axis symmetry is equal is only radial variation in TR. Boundary conditions at center r is equal to 0. Symmetry dt by dr is modulus of r is equal to 0. At surface r is equal to capital R, tr is equal to ts. Step 2, shell balance in cylindrical coordinates. From radial symmetry in cylindrical coordinates, the steady state heat equation with internal generation is 1 by r d by dr into r dt by dx is equal to minus q dot k. Multiply both sides by r, d by dr, r dt by dr is equal to minus q dot r by k. Solve the differential equation. First integration, r dt by dr is equal to minus q dot r square upon 2k plus c1 gives dt by dr gives minus q dot r by 2k plus c1 by r. Second integration gives dr is equal to integrate minus q dot r by 2k plus c1 by r dr is minus q r square by 4k plus c1 ln r plus c2. Step 4, applying the boundary conditions. At r is equal to 0, symmetry derivative must be finite. At ln r is minus infinity, r is 0. So to avoid singularity, c1 is equal to 0. At r is equal to capital R, that is tr is equal to ts. ts is equal to minus q dot r square by 4k plus c2 gives c2 ts plus q dot r square upon 4k. Step 5, final temperature distribution. Tr Tr is equal to minus q dot r square upon 4k plus ts plus q dot r square upon 4k gives Tr is equal to q dot by 4k capital R square minus small r square plus ts. Key insights: parabolic temperature profile is obtained here. Maximum temperature occurs at the center, that is T naught is equal to q dot r square 4k plus ts. Uh, in the step 8, all the 5 steps are given nicely. We'll go through the steps and understand the question nicely. Heat conduction in a cylinder with the internal heat energy. Physical setup is step 1. Step 2 is shell balance in cylindrical coordinates. Step 3, solve the differential equation. Step 4 is applying the boundary conditions. Step 5 is final temperature distribution. Let's move to the penultimate question, that is problem 9. Steady state conduction in a sphere with internal generation. A solid sphere with radius r heat generates heat uniformly at q dot. Thus, surface temperature is Ts. Assumptions: steady state, radial symmetry, constant temperature, conductivity. Step 1 is physical setup. A hollow cylinder with inner radius r1, outer radius r2, uniform heat generation q dot, watt per meter cube. Steady state, radial symmetry, constant thermal conductivity, K, boundary conditions at R is equal to R1, T is equal to T1, R is equal to R2, T is equal to T2. Shell balance in cylindrical coordinates. radial steady state conduction with the generation 1 by r d by dr into r dt by dr is equal to minus q dot k multiply rho by r d by dr into r dt by dr minus q dot r by k. Step 3, integrate differential equation. First integration we get r dt by dr is equal to minus q dot r square by q by 2k plus c1 dt by dr minus q dot r by 2k plus c1 by r. Second integration we get tr is equal to integration of q dot r upon 2k plus c1 by r dr is equal to minus q dot r square upon 4k plus c1 ln r plus c2. Step 4. Apply boundary conditions. We use two given boundary conditions to solve c1 and c2. R is equal to r1, t is equal to t1. T1 is equal to minus q dot r1 square upon 4k plus c1 ln r1 plus c2. At r is equal to r2, t is equal to t2, t2 is equal to minus q dot r2 square upon 4k plus c1 ln r2 plus c2. That is the two equation that we have got. Step 5 is solve the constants. Subtracting equation 1 with equation 2, t2 minus t1 is equal to minus q dot r2 square minus r1 square by 4k plus c1 into ln r2 minus r1 gives c1 is equal to t2 minus t1 plus q by 4k into r2 square minus r1 square by ln r2 by r1. Then plug c1 back into either equation to find c2. Step 6. Tr is equal to minus q dot r square by 4k plus c1 ln r plus c2. Constants c1 and c2 are determined from the boundary conditions. Summary. The temperature varies logarithmically and quadratically. Maximum or minimum temperature will depend on the temperature between T1, T2 and the amount of heat generation. These are all the steps that we have got in the problem 9. All the steps we'll discuss all the steps again so that we can understand the problem easily. This problem was based on steady state conduction in the sphere with the internal generation. In the step 1, the physical setup was made us to understand all the given all the information given inside the question were written down in a summarized way. In the step 2, shell balance in cylindrical coordinates. Step 3, integrate the differential equation. Step 4, apply boundary conditions. Apply the boundary conditions. Step 5, solve for the constants. And step 6, final temperature distribution. After final temperature distribution, the temperature varies logarithmically and quadratically. Maximum or minimum temperature will depend on the relation between T1, T2 and the amount of heat generation. This is the last question. Problem 10. That is transient heat conduction in a cylindrical unsteady 1D radial derived the unsteady heat conduction equal equations for a solid cylinder. Step 1, physical setup. A solid sphere of radius r, uniform heat generation q dot, thermal conductivity k, radial symmetry steady state, boundary condition dr is equal to ts, symmetry at the center dt by dr, modulus of r is equal to 0. Step 2, governing equation, that is spherical coordinates. Radial shell balance for a sphere with internal generation 1 by r square into d by dr into bracket r square dt by dr is equal to q dot k. Multiply both sides by r square. D by dr is r square dt by dr is equal to minus q dot r square by k. Step 3, solve the differential equation. First integration r square dt by dr is equal to minus q dot r cube by 3k plus c1 gives dt by dr is equal to minus q dot r 3k plus c1 upon r square. Second integration tr is equal to integrate bracket minus q dot r by 3k plus c1 by r square into dr is equal to minus q dot r square by 6k minus c1 by r plus c2. Step 4. Applying the boundary conditions. At r is equal to 0, symmetry dt by dr and modulus of r is equal to 0 must be finite. But c1 by r2 at infinity at r is equal to 0, so c1 is equal to 0. At r is equal to capital R, tr is equal to ts. Ts is equal to minus q dot r square by 6k plus c2. That is c2 is equal to ts plus q dot r square capital R square by 6k. Step 5. The final temperature profile Tr is equal to minus q dot r square by 6k plus ts plus q dot r square capital R square by 6k is equal to Tr is equal to final q dot by 6k into bracket capital R square minus small r square plus ts. Key points. The temperature is parabolic in radius r. Maximum temperature at center r is equal to 0. T naught q dot r square capital R square upon 6k plus 0 ts. First, we'll understand all the steps again for the 10th question. That is, this question was a transient heat conduction in a cylinder, unsteady 1D radial. Step 1 is equal to physical setup. Step 1. Step 2, governing equations. Step 3, solving the differential equation. We have to equate it integrate it two times. That is q dot r by 3k plus c1 by r square, and other time we get q dot r square by ck 6k minus c1 upon r. In the step 4, we applying the boundary conditions, we get the value of ts. We get the value of c2 is equal to ts plus q dot capital R square by 6k. Step 5 is final temperature profile. Tr is equal to q dot by 6k into capital R square minus small r square plus ts. The key points here are the temperature is parabolic in radius r, maximum temperature at center r is equal to 0, and T naught is equal to q dot capital R square by 6k plus ts. I have explained 10 problems here in this following video. All the 10 problems were various conditions for the shell balance, and heat generation. Various conditions were explained here. Various questions were about 10 questions were explained. All the questions had a different steps in it. Five Every question had 5 to 6 steps. Uh, all the steps are explained properly. Thank you, and I'll take your leave. Have a great day ahead.